By the way, this is an aside, but the question is, why does that work? Why is there a dimensionless number that determines whether something is laminar or turbulent? So in this case, I'll give you a preview of why this works. Basically, what I claimed was that turbulence is really sort of a consequence of having so much inertia that you're destabilizing a flow. Well, if inertia destabilizes a flow, what is it that does stable, or what is the stabilizing force that normally would keep it stable? And the answer is shear stress. So, like, viscous dissipation is the thing that actually damps down any perturbations in the flow that like cause sort of inertia-driven vortices. And so the way that you can sort of rationalize this is that inertia can be sort of converted to a pressure, like a driving pressure that helps destabilize things. We haven't seen this yet, but there's something called Bernoulli's principle, or I guess it's Bernoulli's, I don't know, equation. I don't know if it's not really a law, it's more of an equation. So in the absence of viscosity, you can basically have this interdependence between velocity and pressure. So we will come to this soon enough, but pressure plus half rho v squared, it turns out to be a constant when there's no viscosity. So if I didn't have viscosity, you could basically interchange, like if you had a flow pattern, you could have areas of the flow pattern where the velocity was high, but then if that same flow ever came to a stop, then the velocity would have been converted into a pressure. So what Reynolds number is basically a comparison between the size of the pressure forces in a fluid that are due to inertia and the shear stresses that exist. So we've already sort of seen that the shear stresses that exist in a fluid basically they're proportional to the viscosity and the velocity gradients. So like in a pipe flow, for example, that velocity gradient would go as the velocity, like you could work out the formula, for example, for the flow pattern, but you'd always come to the conclusion that that velocity gradient goes as the velocity divided by the diameter. That's the characteristic scale that the velocity changes, like that's how much the velocity changes, and the characteristic scale over which it changes, right? So like if I just think of v divided by d as the derivative, like the scale of the derivative of du dy, for example, and then compare that to what you would get from Bernoulli's equation, you arrive at a dimensionless number which is exactly the Reynolds number. So this is basically how the rationale between how you would form that dimensionless number works and why it would explain whether the flow is laminar or turbulent. Basically, when inertia forces are much bigger than the damping forces, that causes instabilities to grow beyond repair.